Good morning, everyone. Let's start the second lecture about memory management. Okay, so here you can see that the topic's 5A, okay, because this is for the theoretical part, talking about memory management in general. And we do have a set of slides called 8B, okay, that will be dedicated for our XP6 operating system. Okay, all right. Let's start. This is the outline for today. Okay, first of all, I'm gonna talk about the background. Okay, why we need memory management. Okay, and then for memory management, actually, we do have different allocation method. The first one is so-called contiguous memory allocation. The second one is called paging. Okay, and paging is very interesting and important for modern operating system. And I'll also talk about the structure to implement this paging. And then after that, I'm gonna talk about swapping. And then I think for the next topic, I'm going to talk about virtual memory, which is about an efficient swap. Okay. All right. Let's see. Okay, this is the learning objectives. So after this section, you should be able to provide detailed description about different ways of organizing memory and discuss about memory management techniques. Okay. All right. So let's see the background first. So we know that CPU can only access registers and memory directly. Okay, the CPU cannot directly access your disk. So this means that your program, if you want to run your program must be brought into memory before execution. And then, when in your program, you may try to do some operation, do some computation. You may need to read the data from the memory, and then you may later on, after you do the computation, you may need to write the result back to some place in your memory. So actually, I'm going to talk about this memory unit. Okay, this is between CPU and your memory. So memory is in between, and then actually this memory unit only sees a sequence of operations regarding memory, either read or write. Okay, later we're going to see this. And the register access is very quick. It's just in one CPU clock. Okay, so it's very fast. However, if you want to access memory, it will be much slower than register. Okay, so it may take many CPU cycles. So during this read operation or write operation, the CPU will have a stop, meaning that it has to wait until the memory access to be finished. Okay, so this is not efficient. So that's why we have some so-called cache between memory and CPU register. Okay, so different CPU architecture may have different size of this memory cache. And the last important thing is that memory is very important, so we need to protect it. Okay, for example, you need to protect the system operating system memory against the user program memory. Okay, user program memory cannot access the memory maintained by the OS kernel, right? So we need to have this protection. And if we want to do this protection, what kind of things that we need to do and what kind of support are provided by a CPU? Let's see this. Okay. So for the protection, actually, we need to make sure that a process can only access its own addresses, right? You cannot access the other address space for other processes or even the kernel, right? So how do we ensure this? Okay, to provide this kind of protection, actually, we need this kind of register. We call it base register and the limit register. Okay, so as this figure shows, okay, let's say this is our memory, right? And then this process is here, right? So it starts from this number until this number. Okay, so meaning that this process can only access, let's call it process A. Process A can only access this region of your memory. And how do we protect? How do we do the checking for this? Okay, here we have this so-called base register indicating the starting address of this process. Okay, and then we have this limit register. Basically, limit register stores the value of the length of this process. Okay, so meaning that base register, the value of base register plus the value of limit register gives you the ending address for this process. Okay, so these registers are provided by CPU actually. And whenever you want to access the memory for one process, right? The CPU, for example, CPU say, okay, I want to access this address because this CPU is owned by some process now, and the process wants to access memory. So the CPU will issue this, let's say, memory read, and then we need the hardware will do this checking. First of all, we're gonna check whether this address is bigger than or less than the base address. Okay, base register. Okay, so if it is yes, it means that okay, this is above here. Okay, this is above here, so it is within the legal range. Okay, so we can continue. If it is not, okay, if it is less than base register, it means that you're accessing the memory access in this region below this. So this is illegal. So you're gonna have a trap. Okay, meaning you have an error. Okay. And let's see this branch. Okay, the address is bigger than the base register. It means that it is okay. It's above this line. Okay, but we still need to check whether it is below this line, right? So we need to check whether the address is less than the base plus limit. If yes, then okay, this is a legal memory access. If not, then we're gonna have another trap. Okay. So since these two registers are provided by the hardware and only the operating system can access these two register, okay? And usually it will be via some special privilege instruction and only in kernel mode. Okay, any questions so far? So this is how we protect memory access by using the two registers provided by the CPU. Okay. By the way, if you have questions, you can type your questions on in the chat panel. Okay, one student is asking what this graph means. Okay, this is just a flow chart to check whether a memory access is legal or not. Okay, so for example, if let's say some process wants to access this process is process A. Let's say this range is owned by process A. And let's say if process A wants to access this region, then this will be illegal, right? But how do we check this? We need to use this base and limit register to check that. And this flow chart is the steps that we're going to use based on use these two registers to check whether this memory access is within the legal range. Okay. I hope I have answered your question. Any other questions before I move on? All right, now let's move on to the next topic. So here I'm gonna talk about when you write your program, you want to execute your program, what are the steps that are typically done? Okay, so for example, you have your source code here. It could be in C or C++, right? And then you need to use a compiler to compile your source file. And usually the output will be your object file, right? And this is considered as your compile time, okay? And let's say, okay, after your compilation, right? And then you may need linker to link. For example, in your program, you're using some library, okay? And then, for example, read and write files, this is the library, okay? So if you use this kind of API, right? Then you're calling some functions provided by library. And in this case, you need a linker to link this object, library object file together with your programs to have your executable file. Okay. And after that, you may start to run your program, right? So you need to, for example, in the shell, you can type your program name, and then and after that, you're telling OS, okay, I want to load my program into memory for execution. So OS has this so-called loader. It will load your executable file in memory and do the execution. Okay. So basically, these are the three phases: compile time when you compile your program, and then load time to load your program into memory, and for the execution, we call this the execution time. Okay, so during this steps, the three steps, you need three tools actually. You need a compiler, you need a linker, and you need a loader. And basically, compiler and linker is provided by your programming platform. For example, GCC provides this C compiler and as well as a linker. And loader is usually provided by the OS. Okay? I'm sorry. And then after that, we have these three phases, right? I also want to talk about this address binding. Okay, we know that if you want to run your program, you need to bring your program executable file into memory before execution. But the question here is where are you going to bring your program in the memory? Okay, so deciding where to load your program is called address binding. Okay. So this address binding can happen in different phases. Okay, so first of all, let's understand what are the form of your addresses. Okay, actually, in different phases, you could have different form. Usually, in the source code, when you do the program, right, you write out when you write your program, when you want to access a variable, usually the memory location will be symbolically. Let me try to draw it like this. Okay. So in your program, right, you need a variable that's an integer x, right? So usually this x will be loaded in memory somewhere. But when you do the programming, you don't know. Actually, you don't care about where it is allocated. So usually in your program, you will say, okay, when you say x, it means somewhere in the memory, but I don't know where. But it's an abstraction. Okay, it's an symbolic representation of this memory address. And you can read or write. For example, you can say, I want to assign 5 to this variable. Okay, so this is in your source code phase. Okay, so X is actually a memory location. But for a programmer, we don't care where it is. We just want to treat it as a symbolic representation. It's X. Okay, but during the compile time, you need to some sort of assign an address to this variable. For example, this X is located in the 14 bytes starting from your program. Okay, so this is what is done by the compiler. Okay, meaning that your symbolic representation, this variable name becomes a number, an address. Okay, this is not the absolute address. This is a relative, okay, relocatable address. Okay, starting from the beginning of your file or beginning of your module. Okay, then we're going to see an example. I'll show you an example. And after that, you do the linking or loading, right? So this 14 bytes is you can think of it as an offset from starting from your file. But when you do the linking, you want to load this file, this executable into the memory. You need to know the exact address because you want to load it to some place, right? So you need to know the exact address. So this address will be translated into a real address number. Okay, so you can see that this address binding would happen in different phases, and you will be translated from one to another. Okay, so let me show you an example. Okay, I'll show you step by step. So previously, I've been talking about that. Okay, address binding can happen in compile time, load time, and execution time. Right? Let's see what will happen during each phase. So in the compile time, right? The address binding is done in compile time. It means that you already know where are you going to put your executable file in memory. So you already know the absolute address. So in this case, the absolute code will be generated. Okay, so what does it mean? Okay, let's give you a very concrete example. So let's say you have a program like this. Okay, so you have a several statement, and after that you declare a variable integer x, and after that you want to assign value 5 to this variable. Okay, very simple program. And then so after that, right, you do the compilation, but you already know where you are going to put this file, this executable file in the memory. For example, here, you want to put it here, and here this address is 100. So you need to tell the compiler, hey, my program wants to start from 100. So you need to let the compiler know this information. Okay? And after that, the compiler will give you a file like this. Okay? This operation will becomes this. Okay, I'm going to use this bracket to say, okay, this is the address in the memory. Okay, so this will be, let's say, this variable x is starting from the 14 bytes from your program. Okay, so it means that you're going to put 104. You're going to assign value 5 into this address. I'm sorry, 114. So it should be 114. Okay, because your program starts from 100, and this variable is in the place 14 bytes starting from your program. So its address should be, let me try to make it clear. So this should be 114. Okay, because you want to start from 100. And this X is in the 14 bytes, so its address should be 114. So meaning that your program will be compiled as this form. Okay, so this 114 is the absolute address. So we call this the absolute code. Okay, in this case, loader can help you to load your program into this address here. Okay, then this could cause an issue. What if you want to, you want to load your program in a different places? For example, 200. Maybe I should put it here. Okay, 200. You want to load it here. What do you need to do? You need to change your code as this, right? 214. You want to assign 5 to the memory address 214, right? But how do you do this? You need to recompile your program. Okay, you need to do the compilation again. And you need to let the compiler knows, hey, I'm gonna start from 200. Okay? So this is when we want to do the address binding in compile time. Okay, you can observe that this is kind of restrictive, right? Every time you want to load your program into different memory address, you need to recompile your file. Okay, so this is not that convenient. Okay, any questions so far before I move on to the next slide? Okay, I don't see any. So this is when we do the address binding in compile time. And what if we want to do the address binding in load time? Okay, because I'm not sure. For example, I'm not sure where I'm going to put my program in memory. So I'm not sure. So in this case, we need to generate our code as the relocatable code. Okay, I'm going to use the same program. Okay, so this is our program. Again, we have integer x declaration, and after that we want to assign x. I'm going to use the standard. Okay, you know this. I use this arrow meaning that, okay, I want to assign 5 to this variable. Okay, and that's it. Again, this x is located in the 14 bytes, starting from your file. Okay, so now I don't know where I'm going to put my program in, so we need to generate this so-called relocatable code. So this is what will be generated by a compiler. Okay, so you do the compilation. It will be like this. Okay, so you're gonna have your starting address. We call it base. Okay, and then here it would be base plus 14. Okay, so this instruction, this operation will be, sorry, I'm not sure whether you can see my cursor. Let me check. Okay, so this operation will be translated into this kind of form. Okay, B would be your starting address. We call it base address of your program. Okay, and then we know that X is located in the 14th byte starting from your file. So your address should be B plus 14, right? And you want to assign 5 to this memory location. Okay? Then what is the good thing about that? If let's say you want to load your program starting from 100 here. Okay? So the loader will just set B to be 100 and your program will be here. Okay? So this, I'm gonna use this, sorry. Let me think. Okay, so your program will be loaded here, let's say. Okay, and then this your statement will become 114. Okay, so the loader will help you to fill in this B value here, the base address, so that your code becomes like this. Okay, then what if you want to load your program in starting from 200? You just tell the loader, okay, I want to start from 200. And then the loader will do something like this. Okay, this is 200. And then you will change this operation to 214. Okay, sorry, my handwriting is too ugly. Let me rewrite it. Okay, this would be 214. Okay, so you can see that you don't have to recompile your program anymore. You only have to compile it once. And since the program is generated as the relocatable code, so every memory access or memory is relatively to this base value, base address. So it can be relocatable. Every time you want to relocate to some different starting address, you only have to tell the loader, telling that, okay, my starting address will be this number, and the loader will change the address for you automatically. Okay, you don't have to recompile your file. Okay, any questions? Before we move on to the next slide. Okay, I don't see any question. Good, let's move on. So the next option is that, okay, we want to bind the address in execution time. Okay, this is the most flexible one. This means that, okay, when you execute your program, you can actually move your program from one memory location to another. Okay, so actually this is what is done. Okay, I'm gonna use the same program. So you have integer x here, and you want to change x to 5. Okay, so here again, this is 14 bytes. Okay, so for the this is when you do the compilation, the compiler also generates this relocatable file as well. So this is b plus 14. You want to change the value to 5. Okay, so if we do the address binding in execution time, actually when you load the program, right? So for example, this is 100. It doesn't matter. Actually, the program is still this. Okay, in your program, in the memory is still this. Okay, actually this doesn't matter. Okay, I'm gonna change it. So this doesn't matter. It could be B. Okay, so in the memory, you still have this relocatable file. We don't change the B to a specific value. No. Okay, and then let's say, okay, the CPU execute until this statement. It will check, okay, what is the current B value? Okay, and then we do the calculation. What is the current B value? We do the calculation. We know where is this actual address, and we do binding until this time. This is at the runtime. Okay, and then we know this address at runtime, we go there to do the modification. Okay. And the good thing about this is okay, you can move this to somewhere else. It doesn't matter as long as you know the current value of B when executing this program, and this should be fine. Okay, and of course you need hardware support for this. What is this B value? You need some hardware instruction to get this value. For example, your base register, your limit register, etc. Okay. And in paging, you have this page table number. We're going to talk about this paging later. But anyway, if you do the address binding in execution time, the actual address is decided at runtime. Okay? Any question here? I hope I have clarified the concept of address binding in different phases. Okay. Jacob is asking, will the CPU have to use more cycles to calculate each variable address? Well, modern CPU do consider this, translation, So for virtual memory, for paging, yeah, of course, it will cost more cycles, but you bring the flexibility. Okay. So another question is, okay, thanks. Another question is that what is the difference between load and execution time? They both, yeah, indeed, they both of them use relocatable code, but the difference is that okay, in execution time, when you load the program into the memory, you still have the relocatable code. Okay, but for load time, when you load the program into memory, the code is no longer relocatable code. Okay, the loader will replace this B value into some specific value. Okay, so you can see that here, this is the load time. Your program looks like this. You already have a specific value here. But for address binding execution time in memory, you still have this relocatable form. Okay? I hope I have clarified this part. So as mentioned by Jacob, there's address binding execution time. CPU may be complicated. You could have more cycles to do that. But the good thing about that is that you have flexibility. Your process can be moved around. Okay, maybe we know that you have priority scheduling, right? So if the process has lower priority, you can swap out this process to this and then swap in back, right? So this, if you want to achieve this, you need to have this address binding execution time. Otherwise, you need to load this process at the same address, right? This is not common. Maybe that address is occupied by other process already. So it will be very difficult and challenging to do this movement. But if you do the address binding in execution time, it doesn't matter. You can put your address in different memory location. That is fine. It's more flexible. Okay. All right. I hope we are clear. Okay, I see one more point. Does that mean for compile time and load time, the CPU is consistently being used by the process? What do you mean by constantly being used by the process? So for the compile time, right? Like it's not swapped out by the scheduler. Yes, if you are doing the address binding at compile time or load time, right? Once the program is loaded into memory, you cannot change that. Okay, it has to be there. It has to be there. Okay, so let's say I think Junmin, right? If this is the case, let's say you load the program into here. This is the relocatable file, but we do the address binding in load time. Whenever you load this, you need to load it because you need to tell, because we do the address binding at load time. So every time you load the program, you need to tell the loader where are you going to put this memory address. Okay, so after that, the loader will do that. and after that, the code will become absolute. Okay, so if this, let's say if the CPU, the OS is swap out this process, okay, and then when you want to load this, you need to either, okay, you don't tell the loader where you still because the code is like this, right? It has to be loaded into the same location, unless you tell the loader, so, okay, I want to start from another address, so you tell the loader, okay, 200, and you load it here. Okay, but this is complicated as than this one, because this one you don't do this kind of complicated, calculation. Okay, you need to tell the loader, okay, I want to have a different address, like that. You don't need to do that. It's decided at runtime. Okay, Jimin, I hope I have clarified your questions. Okay, good. Who does the decision during runtime? OS. Okay, 是前, right? And OS will do that. Oh, you mean the decision, right? The decision is fixed. For example, let's say if you're using x6, right? It knows that, okay, we are going to use the address binding at execution time. It is fixed when the OS is designed. So whenever you want to use some specific OS, the OS already decided. Okay? And actually, modern operating systems adapt this address binding and execution time. Uh, so Young, right? I mean, this example are general high level to let you understand, the concept. Of course, some address, for example, 100 may be occupied by IO. So you cannot do that. Okay, of course, I'm talking about general high level concept. I'm not talking about specific. Okay, this address cannot be used. Yeah, of course. In specific, some lower value address cannot be used directly. This is mapped to IO, of course. Yeah, you're right. Okay, but let me highlight this example here is just for illustration of this three different address binding. Okay, the actual value 100, 200, this may not be valid in some specific operating system. Okay, so this is just for illustration, easy illustration. You're right. 100, 200 is not available for general purpose program. It is allocated to some memory map IO. You're right. Okay, any other questions? All right, now let's move on to the next concept. Okay, so here I want to differentiate two terms, logical address space versus physical address space. Okay, so the concept about logical address space is that, okay, for every program, for every process, you have your own address space. We call it logical address space. And usually the logical address space starting from address 0. Okay, this is logical to this process. It's not the actual physical address. Okay? So whenever, let me try to draw this. Okay, so let's say you are the programmer, you write a program, right? And then let's use the same example. Okay, you have integer x, then when you want to assign 5 to this variable. So once you compile this program, you have an executable file. Okay, and usually, and we draw it like this. Okay, this is 0, and this is the end of your program. Okay, so this is logical address. You can think of this as your base. Okay, so this is your logical address space starting from 0, and then all of your program is growing like this. Okay, so every process has its own address, logical address space. Okay, and if every process think of, okay, my logical address space belongs to myself only, no one can access that. Okay, that's why we call it logical. Okay, and whenever the CPU execute your program, right, it also generate logical address. So for example, that's what I'm talking about, this address binding in execution time. So whenever you want to do this, right, you have this B plus 14, right? You want to access this file. So it will generate, for example, CPU want to execute this. You will say, okay, I want to access logical address byte 14, okay? And then this will be translated into physical address by MMU. Later on, I'm gonna talk about this. Okay. So that's why we call it logical address. Okay. And then we know that memory, we only have one memory, right? And every process as well as the kernel share this memory. So the address for this actual memory, we call it physical address. Okay, so this physical address will be seen and translated by the memory unit, MMU. Okay? Any question here? So if we are doing address binding in compile time as well as load time, actually these two address space doesn't, they are the same. Okay, the only difference when you do the address binding in execution time, because this may refer to some address. Okay. Any questions here? Okay, I'm gonna say again. This logical address and physical address will be different only when we do the address binding in execution time. Okay. And then we have another terms called logical address space and physical address. Logical address is just one address, okay? And logical address space is the set of logical addresses that can be accessed by the process, okay? And similarly, physical address space is a set of physical addresses. Okay? Any questions here before I move on? All right, now let's move on. So this figure shows you the so-called memory management unit. Okay. So when CPU execute your program, right? Because CPU, when CPU execute your process, the current process owns the CPU, and the CPU execute your program. Actually, CPU will generate whenever the CPU wants to access the memory address, right? It will always generate the logical address dedicated for this process. And where is this actual physical address? This will be decided or translated or handled by MMU. MMU will help you to translate, okay, where is this actual logical address? Where is this physical address? And it will translate this logical address to physical address and then go to the physical memory, the physical address location to retrieve or read or write that memory. Okay? Any question? So this MMU, actually, there are a lot of ways to implement this the MMU, and we're gonna talk about some of them in a moment. Okay. All right. Let's move on. So let's consider the most simple one. Okay, we can use this base register and limit register. So if here we have a different name for base register. Sometimes it's also called the relocation register. Okay, so its idea is like this. Okay, when the CPU says, "Hey, I want to access address number 346," this is logical, right? Where is this, located? So it will goes through this MMU, and MMU knows what is the base register or the base value, base address for this process. Let's say the base address is 14000, and then after that, it's easy, right? We just have to add it. So this logical address is kind of an offset starting from your address, your logical space. So we only have to add the value of your base register, so you have your physical address. Okay, and then this will be your physical address in the memory. So we go to this address to read or write. Okay, so meaning that your user program only deals with logical addresses. You never know where it is. Okay, only MMU knows. MMU will help you to do this translation. Okay. Any question here? All right, now let's move on. Okay, here I only talk about the more simpler one. So use this base and base register and limit register, right? Later on, when we talk about paging, we have this, address translation. This MMU is actually implemented by page table. Later on, we're gonna see this. Okay. All right, let's move on. So now I'm going to talk about this concept, so-called dynamic loading. So usually this will be done by the user program, not by the operating system. Okay. So when are we going to use this dynamic loading? It is, in a scenario where your program is very big, but some of the procedures, some of the functions are used rarely. Okay, so for example, you have your program handling user input. Let me draw it like this. Okay, so you have your user program, handling the user input. And then the user input may have several error scenario, and you have some error handler. For example, you have this. This is your error handler. Okay, but let's say in real case, user input the data correctly. So this error handler are never used. In this case, it will be a waste if you try to load the whole program into your memory. Okay, so in this case, this part is rarely used. So maybe we don't want to load this in memory first, okay, until we need it. Okay, so this is called a dynamic loading. Only the main part is loaded into your memory. Okay, and this error handling, this routine is loaded only if it is needed. Okay, and in this case, we can have better memory usage, memory utilization. Okay, and in this case, of course, your program needs to will be kept on disk in relocatable form. Okay, because you may load it in some if needed, it will this error handler will be loaded into memory if necessary, right? So you don't know where you're going to load it when you compile the program. So they will be in relocatable form. Okay, so it will be this will be very useful when your program is big. Okay, and the error handling procedure will be used infrequently. So this will be a good approach. But the bad thing about that is that, okay, no special support for your operating system, meaning that your operating system doesn't provide you this kind of feature. The programmer needs to take care of this dynamic loading by themselves. Of course, always can help you to provide some library to do this. But the logic, when and where to load this error handle, this will be decided by the programmer. Okay? All right, let's move on to this so-called dynamic linking. Okay, dynamic linking will be supported by operating system. Okay, but before I talk about dynamic linking, I need to talk about static linking first. Okay, it's because static linking is not efficient, so that's why we want to have dynamic linking. Okay, so what is static linking? Okay, imagine you have we have three programs. Okay, we have let's say we have a library here. And we have three programs. They are going to use this library, the same library. So let's say this is process A. Okay, they are going to use this library. And process B or program B, it also wants to use this library. Another C program also wants to use this library. Okay, so if we're talking about static linking, it means that okay, the binary of this library will be combined together with your executable. Okay, and similarly for B as well. So all the binary file for these three processes have this library. So imagine if you want to load the three programs into memory, then you're gonna have three duplicate library. They are the same. Okay, this is a waste in memory. So we don't want that. We don't want to have exactly the same library appearing in the memory for many times. Okay, it's not efficient. So that's why we want to have this dynamic linking. Okay, so for dynamic linking, again, we have this library. But for process A or program A, instead of including all the binary files for this library, we put a stop here. Okay, so this is process A, and process B we also have this stop. Okay, and process C we also have this stop, and this stop will be much smaller than this library binary file itself. Okay, so this stop is a small piece of code used to locate where is this library is. Okay, so meaning that in memory you have A, so you have a stop here, and you have B, you have stop here, and you have C, you have stop here, and the library is loaded in the memory somewhere here. Okay, and then this stop is to help to locate this line. For example, whenever you want to execute this library, you will go to here for the execution. Okay, it will be like this. It's kind of an indirect invocation. Okay. And then, of course, this stop will communicate with the OS. So, for example, when you execute this until this stop, it's kind of a system call. You can think of it like that. Every time you want to execute this library, you generate system call, notify the OS. That's the OS is here. Okay, then the OS will tell you, hey, this library is here, is somewhere in the memory. It will gives you the address. Okay, and then if you know the address, you can go to the exact library and invoke it. Okay, and of course, if the library is not loaded, OS will know that, and it will help you to load the library into the memory. Okay. So dynamic linking is very useful for shared library. Actually, in Linux, it's SSO file. This is the shared library. It's used this so-called dynamic linking technique. Okay, and it is also very useful when you want to patch your system. So, for example, this library, okay, we have version 1, and now we have an updated version. It's an improved version, library version 2. So, right? In this case, you only have to patch this library once. Maybe in the OS, you patch it, right? And then whenever the program need not to be changed, whenever the program wants to invoke this library, it will ask the OS saying that, hey, give me the where it is. And the OS will know, okay, the latest version is somewhere, and it will return the address to the program, and the program knows where to find the latest improved version. Okay, so this is the good thing about dynamic linking. Save the memory usage, and as well as it's very convenient. Okay, any questions here? All right, if no, let's move on to the next concept. Okay. All right, we know that memory will be shared by kernel as well as different user process. So we need to allocate memory to, either kernel or user process. So how are we going to allocate this memory to different processes? We do have different approaches. The first one is called contiguous memory allocation. Okay. Oh, this is just what I just said. Okay. Memory are limited, but they will be shared by OS and user process. So how are we going to allocate this? So now I'm going to talk about this contiguous allocation. It's a very old method. Okay. So as the name implies, you know that whenever you allocate memory to a process, you always allocate contiguous, consecutive memory to a process. Okay. In this case, actually, your main memory will be, split or divided into different partitions. Okay. And operating system is the most important one, right? So you will have, so it'll be like this. Let me draw it. So this is your memory, right? Okay. And then this memory needs to be shared by OS and processors. So usually we will allocate the low region, to OS. Okay, this part will be to OS, and the rest can be shared by user processors. Okay, so this is the idea. And usually this part will be allocated to interrupt vector or memory map IO, etc. So OS will use this portion. Okay. So this is about contiguous allocation. Because the space is allocated contiguously, right? So as I mentioned previously, we do have this base register and limit register, right? We can use these two registers to protect the memory for one process. Okay. And actually we do have a statement in textbook. So it says that each logical address must be less than the limit register. I'm gonna think about why. I'm gonna explain this later. Okay. So for contiguous allocation, MMU can help you to translate this first logical address into physical dynamically. So this is the flow. Again, we have a flow chart here, right? So whenever CPU wants to access a memory and given the logical address, you can see that now the flow chart is like this. We compare this logical address with the limit register only. We don't compare with base register. Why? Think about why. So let me try to draw it here. So this is your user program, right? And then logical address space, always start from 0, right? Maybe okay. So this will be your base register, okay, and this is the length of your program, and your limit register is actually uh, hold the value of length, right? So whenever you have a logical address here, right, we only have to compare. We don't have to see whether this is less than limit register. Why? This is because the base register, I should say, logical address starts from 0. So where is this byte? This will actually be your length, right? -1. This byte, right? So whenever you want to check, okay, whether this logical address is valid or not, you only have to compare with this number, limit register. You will know the length of this range. Okay, and if this is less than, we see whether the logical address is less than this value. If yes, okay, it will be within this, right? If not, it means that it's go beyond this, so it will be an error. So you're gonna have a trap. Okay, so if it is less than here, it's here, it's legal, and then we try to this relocation register. So because 0 is the logical starting address. Now we are going to translate this logical into physical. So you need to know the relocation base register. It could be some value, for example, this number or this number, and you need to add with your offset. Okay, your logical address you can think of it as an offset. Okay, so this offset added with your base starting address, you know the actual physical address, okay, and you can go to the actual address to access. Okay. Any questions here? So this is how we use this hardware support to do this, relocation for contiguous memory allocation. Okay. I think let's take a break for 4 minutes. Okay, let's get back at 12. I'm gonna continue from here. Okay. All right, let's continue. Okay. All right, so now I'm going to talk about this so-called variable partition. So we know that the memory will be shared by OS kernel and different processes, right? And different process will have different size, right? So in this case, the memory will be partitioned into different, we call it variable partition because the size of every partition will be different. And here we are talking about this degree, right? Degree of multi-program. How many processes are executed at the same time in your kernel? So this will be, limited by the number of partitions. For example, in the memory, you only have 10 partitions. It means that, okay, including the OS, you can have at most 9 processes, running in parallel. So this will be the degree of multi-programming. And in contiguous allocation, we do use this hole to refer to the available memory. Okay, we call it hole. Okay, so it will be like this. Later on we'll go through this example. So when a process arrives, right, it is allocated the memory for a hole large enough to accommodate it. And when the process finish, the process will exit, right? Then its memory will be released to the OS, and the OS will see, okay, if this space is adjacent to some other free holes, then it will be combined. Okay. So and actually OS needs to maintain what are the allocated partitions and what are the free partitions. Okay, to fulfill the request for the processes. Let's see an example here. Okay, so you can see, okay, this is now the current snapshot of our system, the memory. Okay, OS is here, and then we have 3 processes in occupy this region of memory. And let's say, oh, okay, after that, a process 8 finish, so it exit, and its occupied memory will be returned back to the OS. So the OS will mark it as, okay, this is free. Now we have a big free hole here. And after that, let's say process 9 comes in, and then we allocate this region to him. Okay, so now process 9 occupies here. Now we have a smaller free hole here. And then after that, that's a process 5 finish. So it exit. So we now have this free hole now. And because process 9 is here, you can see that they are not contiguous. So we are not able to combine these 2 free holes into a big one. Okay. And of course, once process 9 is finished, we have this free, and then we can combine the 3 into a big chunk. Okay. So now I'm gonna talk about the allocation. When we do the contiguous allocation, right? We do have a question, so-called dynamic storage allocation problem. Let's say, okay, we have a request coming in. It requires size n bytes. Let's say. So let me try to draw it here. It will be easier for. Let's say, okay, this is our memory, current snapshot. Okay. So here we have our 200, let's say, megabytes free. Okay, and this part is occupied. I mark it as like this. And then here we have 100 megabytes free memory, and then this part is occupied. And after that, we have 300 megabytes free hole here. Okay, like this. So that's it. This is our current snapshot. Okay, like this. And let's say we have a request coming in. For example, let's say 75 megabytes. A process requiring 70 megabytes comes in. Okay, and you as the OS kernel, if you try to allocate the free space to this process, what are the choices that you have? Okay, actually we have three choices: first fit, best fit, and worst fit. Okay, so what does it mean by first fit? It means that we allocate the first hole that is big enough. Okay, so in this case, if we are using first fit, so we are going to allocate 200 megabytes to this process. Why? Because let's say this is our order for the searching. Okay, then the first one we see 200 megabytes, and this is enough for 75. So we allocate this to this process. Okay. The second strategy is so-called best fit. Okay, we allocate the smallest hole that is big enough. Okay, so in this case, you need to go through all the available holes and see which one is the smallest one, and it is big enough for this, request. So 200, 100, and 300, which one is smallest one? This one. And this is big enough, bigger than 75. So we are going to allocate this if we are using best fit. Okay. And the good thing about first fit is that you don't have to search the whole available list. Because when you see the first one, which is big enough, we are done. Okay. But for the best fit, because we have a best here, we need to search for the smallest one. So meaning that you need to go through all the available holes and see which one is the smallest one. Okay. But the good thing about that is that it can give you the smallest leftover hole. This is the internal fragmentation. Okay, remember the external and internal fragmentation. We have seen these terms in file system, right? In disk allocation. Actually, the concept about fragmentation is it's a concept about space. Okay, so space can be file system, could be memory. So you will see this term in memory as well. Okay, so here the best fit will give you the smallest internal fragmentation. Okay, so here you can see that if we allocate 200 to this, we have 125 internal fragmentation. If we allocate 100 to this, we only have 25 megabytes as the internal fragmentation, right? Okay, now let's see the third strategy. It's called a worst fit. Okay, so we allocate the largest hole to this request. In this case, for example, in this example, we are going to allocate 300 to this process. Okay, and again, since this is the largest, we want to look. We look for the largest hole. We also need to search for the entire free space, and it will give you the largest internal fragmentation. So you may wonder, why do we want to use this? Okay, so actually this will give you the smallest external fragmentation. And I would say statistics shows that first fit and best fit is better than worst case. Is better than worst fit. Okay, in practice. Any questions so far? I hope I have clarified the concept about first fit, best fit, and worst fit. Okay. Oh, here I'm talking. The slides is here. We have we in memory. We also have external and internal fragmentation. We know about this, right? Let's quickly recall that. What is external fragmentation? So external fragmentation is that, okay, your total memory space is can satisfy the request, but they are not contiguous. Okay, in this case, this is so-called external fragmentation. Internal fragmentation is that, okay, the allocated memory is bigger than the requested. So for example, here, if you try to allocate 100 to 75, this process, we have 25 megabytes as the internal fragmentation. Okay. And here, this shows you some statistical results. So if you always use first fit, right? This is I need to highlight this is in average. This is statistical analysis. Okay, it shows that okay, if you're using first fit, you have this 50% rule. It means that if you have n blocks allocated, you always have 0.5 n as your uh, internal fragmentation. Okay, so this is based on average statistical results, not exact calculation. This is average. Okay, so because we are going to have uh, actually, for contiguous allocation, we will have external fragmentation, right? Meaning that the total space is sufficient, but they're not contiguous, so that you cannot allocate the space to any process. Okay. How do we solve this problem? As I mentioned previously in file system, you need to do compaction. You need to move this block, here and there. For example, let's see here. So let's say we have a bigger process coming in. It requires this number, the summation of these blue parts, right? But they are not contiguous. You cannot allocate it to this process. What do you need to do? You need to move this part to here so that the blue part will be contiguous, and then you can allocate it to the process. Okay? So this is why we need compaction for contiguous allocation. But this will be expensive because imagine you need to move byte by byte. It will be very expensive. Okay, that's why contiguous allocation is not used by modern operating system anymore. And of course, for some portion, for example, direct memory map I/O part, we still have contiguous allocation. But for the rest part of a memory, we no longer use contiguous allocation anymore by modern operating systems. Okay? Any questions about contiguous allocation before we move on to paging? This is the main course for memory management. Any questions before we move on? All right, I don't see any. Let's move on to paging. Okay? So previously, we have been talking about contiguous allocation, and it has drawbacks, right? It will have external fragmentation. So we try to avoid external fragmentation. Okay, that's why we need this paging. We try to split our memory into some fixed size chunks. We call it frames. Okay, so usually it will be the size of the frame will be a power of 2. So it could be between 512 bytes up to 16 megabytes. Okay, and the OS has to keep track of what are the free frames. Okay. And here you will see frames and pages. Actually, they refer to the same thing, but the textbook try to differentiate these two. Let me try to draw it. So this is your memory, physical memory, okay? Physical memory, okay? So we try to divide the physical memory into several frames, okay? For example, let's say 512 bytes would be one frame. Okay, so this is a physical address space. But remember, we have logical address space, right? We have this logical address. This is logical. Okay. CAL. Okay, logical memory space. And then we have the same, we split into the same chunk. Again, these two will be the same. Okay, both of them will be 512. Okay, they need to have the same size, but in logical memory space we call it page. In here we call it frame. But actually they are the same concept. It's the fixed size chunk of memory. It's just the difference is that in logical memory space we call it page, but in physical memory space we call it frame. Okay. So in the lecture, if this context are clear, I'm going to use the term interchangeably, but you know what it means, right? So if we're talking in logical memory, we use page, but in physical memory we use frame. But actually, let's see. Okay. All right. So let's get back. So let's say if your program has requires n pages, and then you need to allocate in the physical memory this number of free frames to this process. Okay. And then remember we have this MMU trying to translate your logical address into physical address, right? To do this translation, we need this so-called page table. Later I'm going to introduce this. So it's just a table to give you the mapping between logical page into physical frame. Okay? So here I need to highlight that if we are using paging, right, we can avoid external fragmentation because the memory is divided into fixed size pages. So you no longer have, external fragmentation, but you still have internal fragmentation. Why? Because your process, the size of your process may not be the multiple of the page size. Okay. So let's say the page is 512, right? Bytes. And your process could be, let's say 513 bytes. It could be, right? In this case, you need 2 pages, right? And then you have 500. In this case, let's say if one page is 112, then you have your process has 113 bytes. You have one more byte here, but you still need one page to include it, right? So this is another 512, but your process is here. And this will be your internal fragmentation still. Okay? That is, here it will be 511 bytes as the internal fragmentation. Okay? Any questions before I move on? All right. No question. Let's move on to the address translation scheme. Okay, so this is the job for MMU. Okay, so I'm going to talk about how we do this address translation based on page table. Okay, so your logical address, okay, generated by CPU. So CPU will say, okay, I want to access this logical address. Okay, so this logical address will be divided into 2 parts. Okay, page number and offset. So let's say we have here. Let's say this is our logical address. We have m bits. Okay, m bits. And if you do the calculation, if the logical address is for n bits, you do the calculation, it could, oh, sorry, what happened here? If you do the calculation, this logical address supports 2 to the power of n different value, right? Meaning that you can have 2 to the power of n bytes addressable by this logical address, right? So for this n bits, this is the content here would be your logical address. So when we do the translation, we're gonna cut it in half. Okay, and what would be this part? What would be the left hand side and the right hand side? So you need to decide your page size. Okay, so here the lowest n bits here, this would be your page size. Okay, so this is why we call it page offset. Okay, so meaning that if you want to use n bits as your page size, it means that your page size will be 2 to the power n. Okay, this will be your page size. Okay, so the total number of memory addressable is 2 to the power n. Okay, now you have page size to the power of n. You do the division. This would be the number of your page number. You're gonna have this number of pages, right? So that's why you will have this. Okay, m minus n as Okay, you do the calculation, you're gonna have 2 to the power m minus n pages. Okay, so this number will be here. Okay. Any questions here? So if you let me try to clarify it again. If your address if your logical address is for n bits, you can address 2 to the power of n different bytes, right? And then you can decide what is your page size. You can say, okay, I want to have this n digits, n bits as our page size. So your page size will be 2 to the power of n. And after that, you do the division, you will have the number of pages that you have. It will be this number. Okay? Any question? So if we have this setting, right? This number in the left-hand side, this will be your P number. We call it page number. Okay? And the right-hand side, we call it D. This will be your page offset, meaning that this number will be the offset within this page number. Okay? Any question here before I move on? This is very important. Okay? Then I'm gonna show you a very concrete example, small example, so that you understand what is this doing. Okay? If no, let's move on to paging hardware. Okay? So for paging, right? So as I mentioned previously, you will have this number of pages, right? And then we will need a page table to indicate, okay, this number of physical pages, where does it map to in physical frame? So we need to have this page table here. Okay, so this is how it works. This is a flow. I show you the flow first and then explain how it works. Okay, so let's say this is your logical address, generated by CPU. It says, okay, CPU says that I want to access this address. Okay, as I mentioned, we have two parts for this address, P and D, right? So this part will be your page number. Okay, and we do have a page table. This table indicates, okay, this logical, for example, this logical page is mapped to which frame in the physical memory. So this will have, every entry is called a page table entry. Okay, it indicates your logical page mapping to which physical frame. Okay, so this logical page number P, you need to look up for the page table. This page table will be contiguous, actually. Okay, you can think of it as an array. Okay, and the page number will be your index. You can directly go to this slot and retrieve the actual frame number. Okay, and once you get this frame number, you know which page, which frame is it in the actual physical memory. Then D will be your offset within that page, remember? So you will know this, where this is the starting address of this frame, and then D will be your offset. So you can locate, okay, this address is actually here. Okay, so this is how the MMU works based on page table. Okay, if it is not clear to you, it is fine. Later on, I think two pages later, I'm gonna show you how this works. Okay, all right. Now I'm going to show you some interesting property about paging. Okay, so let's say this is our logical memory. This is process one. Let's say. Okay, so that's a process one requires 4 pages. Right? So this is logical page number 1. Notice that the index starts from 0. So this is page 0, page 1, page 2, page 3. Totally 4 pages are required by this process. Okay? And then we have our page table here. Don't ask me how this page table is arranged. This will be decided by the OS. But let's say the OS decided like this. Okay? So how do we interpret this page table? it means that, okay, here you have index 0, 1, 2, 3, right? It refers to your logical page number. And the value, the entry in this page table indicates the mapping. So for example, this means that logical page 0 is mapped to physical frame number 1. Okay, so that's like this is our physical memory. We have 8 pages, 8 frames, sorry, 8 frames. Okay, so now the logical page number 0 is mapped to physical number frame number 1. So it's here. Okay, and logical page number 1 is mapped to physical frame number 4 here. Okay, you may wonder how this mapping is decided. It's decided by OS. Okay, we don't know how the OS has a strategy to this mapping, but it's not important here for this moment. Anyway, OS will decide this mapping. Okay, so page table logical page number 2 is mapped to physical frame number 3. It's here. Okay, and logical page number 3 is mapped to physical frame number 7. It's here. Okay, so what is the interesting thing about this? You can see that in your logical space, the memory is contiguous, right? Page 0, 1, 2, 3. They are in order. But after the MMU processing, the page table in the page table, this allocation may not be in order, and mostly they may not be contiguous. Okay, so you can see that here, this is your logical view, right? Logical memory space, but this is actually how it is stored, how it is mapped in physical memory. You can see that they are not contiguous, and the order may not be preserved. But that is fine because we have this page table. Okay, every time you want to access page number 2, what do? You look up the table, right? Okay, it's mapped to physical frame 3, so you go to physical frame 3 to retrieve your data here. Okay, so that's the beauty about paging. Any question here so far? So this is the allocation, okay? And this is the step to retrieve the actual, do the address translation. You have your logical address, right? It's divided by page and offset. So that's if you want to access this address, we see which page it is, which logical page it is, and we look up the page table, indicating the actual frame number. Once we get a frame number, we can combine it with the offset to get the actual address, physical address. Okay. Any question here? Let me use a specific example to illustrate this concept. Okay, this example is quite important, so make sure you follow me. Anytime you have questions, let me know. Okay. So this is like this. In our example, we assume that our logical address is for 4 bits only. Okay, so meaning that this is the form of your logical address. It'll be 4 bits. Okay, so you can imagine if we have 4 bits, 2 to the power 4, it would be 16 different address, 16 different address that you can differentiate, right? Then we say that n, it would be 2. N is what? N is, let's go back to here. N is this, the page size. Once n is decided, you already know the page size. It will be 2 to the power of n. Okay, let's get back to this example. So n is 2. Sorry. N is 2, right? It means that our page size would be 2 to the power of 2. Let me write it down. So your page size would be 2 to the power of 2. That is 4 bytes. Okay, so here you can see that this is for 4 character, 4 bytes in your logical address space 4 bytes, 4 bytes, 4 bytes, 4 bytes. And because our logical address is only for 4 bits, right? 16 bytes are addressable. So it will be here. So this is your logical address space. Okay. So here if we write this, right? Actually, this is the actual, let me try to write. So this part will be the prefix of the logical address will be 0, 0. This will be 0, 1. This will be 1, 0. This will be 1, 1. This will be this part. The suffix will be this number. Okay, so let me try to write it down. So this will be 0, right? 0, 1, 1, 0, 1, 1. Okay, so this will be by how do we interpret this? This address, this logical address is 0, 0, 0, 0. That is this byte. And this byte is its address is 0, 0, 1, 0, 1. Okay, so let me try to write down for the all 0, 0, 0, 1, 1, 0, 1, 1. Okay, 0, 0, 0, 1, 1, 0, 1, 1. 0, 0, 0, 1, 1, 0, 1, 1. Okay. So here I'm trying to just write down one prefix. So meaning that this prefix applies for this section. Okay. This 0, 1 applies to this section. This page actually. 1, 0 is the page. So now you understand why we have this, right? This will be your page number. This will be your offset. It's here. Okay. The 4 bytes within the 4 bytes are within this page number 0, 0. They share the same prefix. That's why they are in the same page. This number of bytes, this 4 to 8, 4 to 7, this is within the second page. The page number is 0, 1. Okay, and these are the offset. You can see that the offset is always within 0, 0 to 1, 1. Okay, you can see that they have the same offset here. Okay, so this is how we interpret this logical address, meaning that you can have 16 logical address here. And how do we, and then let's say the OS help us to map this 4 pages into here. So here you can see that page number 0 is mapped to friend number 5. Friend number 5 is, okay, let me try to write out the friend number. Okay, so this is 0. This is friend number. Okay, let me try to friend. Okay, this is 0, 1, 2, 3, 4, 5, 6, 7. Okay. In the example, it says that the physical memory is 32 bytes. Okay, and because the page size is 4 bytes, you do the division, you will find out, okay, in the physical memory, we have 8 pages, 8 frames like this. Okay, and then this page table decided by the OS, okay, deciding the mapping. So logical page 0, which is this page, is mapped to friend number 5, which is here. Okay, logical page 1 is mapped to physical frame 6. It's here. Okay, logical number 2 is mapped to physical frame number 1 here. Okay, and so on and so forth. Okay, now let's try to do the MMU job to translate the logical address to physical address. Let's see one example. Let's say we want to decide where is this byte. So we know that it's logical. Let's write down the logical address for this F. Its logical address would be this, right? 0, 0, 0, 1. Sorry, 0, 1, 0, 1, sorry. Right? Right? It would be here. So its logical address will be 0, 1, 0, 1. So how do we do the translation? Remember, we cut it half, right? So we cut it half. This would be your D, this would be your P. Okay, meaning that this will be your page number, this will be your offset, right? So what is your page number? It's 0, 1. So it will be, this is the binary representation. You can get a value. It will be what? it will be 1, right? So it will be page number 1 here. So you know that it is mapped to page, friend number 6 is here. How do we do the calculation? It's like this. So this is your page size. You know that it's 4, right? Here. And then this number will be your page number 6. Okay? If you this is because this is your page number 6, and each page is 4 bytes, right? And you need to plus it with your offset. Your offset is 0, 1. This is in binary, but what is the value of that in decimal? It will be 1, right? It will be 1. So this will give you the physical address. It will be 25th. I'm sorry. Why? 25th. You can check it. Where is it? It's here. Right? That's 25th. Any question here? So the calculation I'm trying to do here is actually this flow. Okay? This flow. This is done automatically by MMU, memory management unit. So this will be translated automatically based on the calculation that I'm trying to do here. Okay? Any questions here? Make sure you understand this calculation. It will be tested in your quiz. Okay? So make sure you understand how to do that. Let's see one more. Okay? Let's say we want to calculate the actual physical address of this byte, this byte, K for K. Okay, so let's try to write it down. K, what is its logical address? It would be 1010, right? Here, 1010, right? So we do the same. We cut it half. This will be your D. This will be your P, right? So meaning that the page number will be 10. This is binary representation. The value would be 2. Okay, so it will be here, right? And then it's mapped to friend number 1. It's here, right? So if we don't do the calculation, it'll be like this. This is your page size. This is your times your page number plus D. Okay, so the friend number would be 1. So you put it here. Plus your D will be 10. This is in binary. And if this is in decimal, it will be 2. Right? So meaning that the result will be how much? 6. So it will be byte 6. It will be here. Right? Byte number 4, byte number 5, byte number 6, it will be exactly K. Okay? Any question? So this is how we do the MMU translation from logical address to physical address. Okay? I'm gonna pause here, making sure everyone is clear about this concept. Any question? I hope it is clear. All right. If no question, good. Let's move on to the next page. Okay. So here I want to show you some characteristic about paging. Okay. So here let's use this number as an example. Let's say our page size is 2048 bytes. Okay. And let's say here becomes a process. It requires this number of bytes. Okay. So in this case, how many pages are we going to use for this process? You can do the division. Okay, we know that 72766. If we do the division, it will be, because the page size is 2048, right? Plus, right? So this will be your quotient. We know that it will be, if we do the calculation, the quotient will be 35. The remainder will be 1086. Okay. In this case, how many pages are required for this process? Anyone wants to tell me? How many pages do you need? Anyone? 35 or 36? Okay, very good. You need 36 because you need 35 full pages plus one, page which is not full. Okay, so you can see that the last page. Okay, so here you have 5 page 4. Sorry, it's very ugly. Sorry, you have 35. Okay, full. They are full, and the last page, the 36th page is not full. It'll be like this. Okay, so what are this part? It will be this number. Okay, because the page size is 2048 plus this is occupied, so you have this number as the internal fragmentation. Okay, but you will not have external fragmentation because no, we have pages. The space is divided into pages. Every time you need one page, you just take it. Okay, we don't have we no longer have this contiguous problem anymore. Okay, now let's see what would be the worst case. Okay, let's assume that our page size is S. Okay, the worst case for internal fragmentation would be this number. Why? Think about why. Okay, as I mentioned, the size of your process may not be the multiple of your page size, right? So the worst case happens. Okay, let's say this is our page. The worst case happens when your process has just one more byte. Okay, here, just across the border, one more byte. And because of this one more byte, you need to have one additional page for that, and S minus 1. And in this page, only one byte is occupied. And this is S, right? And this would be S minus 1. So this is your worst case for your internal fragmentation. And this is the statistical result. This is average, okay? Meaning that if you are using paging, the internal fragmentation will be 0.5 of your page size. This is quite good already, I would say. Okay, here comes a question. Maybe you'll say, okay, if this is the case, right? If you want to reduce the internal fragmentation, a very naive approach is that, okay, we reduce the page size, right? The smaller the page size we have, the smaller internal fragmentation we're going to have, right? Is it? But the problem is that let's say, if your logical address is fixed, it's n bits, right? If you try to reduce the page size, meaning that this n is small, then remember you have this number of you have this number of pages, right? But you need to, in your page table, you have this number of entry. Okay, meaning that if your page size is small, you're gonna have a lot of pages, and if you have a lot of pages, then your page table will be bigger. Okay, because you need to indicate which logical page is mapped to which physical thread. Remember, so this number would be the number of entries in your page table. So you need to have a trade-off. Okay, if you have bigger page size, you have smaller number of entries, then your page table will be small. Okay, if you have smaller page, then you're gonna have a lot of you're gonna have a lot of pages, then your page table will be huge. So it's kind of a trade-off. You need to see you need to find a balance between that. Okay, so that's why in some operating system they support different kinds of page size. For example, in Solaris, right, they support two different page size: 5 KB for smaller one, 4 megabytes for bigger one. Okay, but I would say if you have different sizes in your operating system, your kernel will be complicated. Every time you want to do the address translation, you need to see which page size are you using first, right? And then do the translation. It will complicate the kernel design. Okay. Any questions so far? Okay, I see one question. Oh, can I repeat the trade-off portion part? Okay, let's get back to this. Let me use a very concrete example. Okay, let's say we have 32 bits. Okay, this is quite common for our logical space, logical address. Okay, let's say our logical address is 32 bits. And then let's say, okay, we are going to use 10, n is 10. Then you can do the calculation. If you have 10, right, your page size will be 2 to the power of 10. This is how many? 1024 bytes, right? Then how many pages are you going to have? You do the division. This will be your number. You're going to have 2 to the power of 32 minus 10. So you have 2 to the power of 22 different pages. Okay? And remember, we need to have a page table indicating this is our page table. This will be from page number 0 until, because you have this number of pages, right? It will be 2 to the power of 22 minus 1. This will be the number of pages that you have. So in your page table, you're going to have this number of entry. Okay? Let's say we have another choice. This n is, let's say, 16, half of the bits, half of the 32. So in this case, your page size will be 2 to the power of 16. How much is it? It will be, anyway, you do the calculation. But let's see the number of pages that we have. It will be 2 to the power of 32 minus 16. It will be 2 to the power of 16, right? Meaning that if we are talking about this case, your page table will be this. You have 2 to the power of 16 minus 1. Okay, minus 1 is here. Okay, you have this number of pages in your page table. You can compare these two numbers. This is much huge than this, right? So in this case, if you try to reduce the number of entries in your page table, you want to have bigger page size. But if you have bigger page size, your internal fragmentation, remember here, it will be 1/2 of your page size. Okay? So it's kind of trade-off. Okay? Any question here? I hope I have clarified your questions. Okay, good. All right, so let's move on to, okay, let me finish this slide. We are talking about free frames, and then I'll stop here. And next time, for next week, I'm going to talk about how do we implement this page table. Okay, we have different ways to do that. It's very interesting. But let me finish this slide only. So, okay, since the memory is divided into pages, right? And initially they will be all free. But after, process will come in and a kernel will need to allocate free frames to process, right? But how do we keep track of which frame is free? So usually we need to maintain a free frame list, a list. We don't care about the implementation. It's just a list, okay? And usually operating system will, in the implementation, we will use a linked list to do that. And actually in XV6, it also uses a linked list. We're going to see this in the second portion of this part. Okay. But anyway, think of it as an abstract. We have a list. It doesn't matter how it is implemented. Okay. It's a list. So let's say this is our current snapshot. Okay. So this is our memory. Okay. And let's say the gray color indicates the free frame. So here you can see that in the free frame list we indicate, okay, we have this number, this frame number is free, 14, 13, 18. They may not in order. Okay, so here we have 5 free frame here, and let's say this is our process. This is our new process. It requires 4 pages. Okay, so this is logical page number 0 to 3. Okay. And then the OS will, because OS knows maintain this free frame list, it can allocate this to you. Okay. And actually the OS will just go through the list. It may not be in order, but that's fine. So it will just, okay, the OS just allocate, okay, 14 to your page, logical page number 0, 13, the second free frame list, the second free frame to 1, and 18 to 3, and 20 to the fourth logical page. So your page table will be like this. So that's why I'm saying, okay, the content of your page table, the mapping is decided by OS. Okay, you cannot decide it. This is decided by OS. Okay, so after that, you can see that, okay, once these 4 frames are allocated to this process, the free frame becomes like this. Okay, now we only have 1 frame left, a free frame left. Okay, and this is the page table. And as long as we have the page table, and maybe we can do the memory translation. Okay, and you can see that they are here for the actual page, for the actual frame here. Okay, so you may wonder, okay, why is this free frame list not in order? This is because process will come in and come out, right? So, the allocated frame may not be contiguous, so they will be not in order. And when the process is out, the free frame will be reclaimed by the OS, right? When they put here, they may not be in order. Anyway, I'm just trying to say that this free frame list may not be in order. This is quite natural. Your memory allocation may not be in order. So that's why your free frame list may not be in order. It's quite natural. Okay? All right, I think I want to pause here because the next topic is to implement the page table. This is quite complicated and interesting, so I'm gonna save it for next week. Any question here before I dismiss this class? All right, if no, that's all for today. Thanks for coming. I hope I enjoyed this section. I'll see you next week. Bye bye.